The topic for today is something I already mentioned last week, which is why we get complex samples from the RTL SDR stick and from most other SDRs. Why do we use complex numbers to perform digital signal processing? What's the advantage of complex numbers compared to real numbers? And why do we have complex numbers in the first place? Because something I mentioned is, if we think about the physics, we have an SDR, it's a receiver, it has an antenna, and the thing which is measured is the antenna voltage, and the voltage is a real variable. So why do we have complex numbers? That's what we are going to do today. And I will also be speaking about something which is important, which is the Nyquist sampling theorem that tells us how much bandwidth we can represent with digital sampling, which is what we do in SDR. So some of you might have heard of this Nyquist sampling theorem. For some of you might be new, but something very easy actually. And then if there is time today, I will do this FM broadcast demo. So this is more or less the same as we did in GQRX, but with GNU Radio. So taking some of what we will have learned in this IQ sampling, we will apply that to FM broadcast signals. If there isn't time, this will be for next week. So in the IQ sampling folder, I have a few flow graphs. I'm going to start with real sampling, which I already have prepared. I have here a blank canvas, and I want to begin by motivating how the RTL SDR stick works. So we're going to build a model for how this RTL SDR device or any other SDR radio in general might work. So what I'm going to do is to increase the sample rate to something fairly high. I'm going to use 40 million samples per second, because that's more or less the maximum that my computer can keep up with in real time with the kind of processing I'm going to do. But since this is really an emulation, so to speak, of a radio receiver, any sample rate might be okay. Then I'm going to pretend we have some signal. So I'm going to use the signal source. And this is the signal that comes into the antenna. So as I have said, signals in the physical world are real. I'm just changing this block to float. So it has a real input. This represents the voltage in the antenna connector. And the most simple kind of waveform we can have is a cosine or a sine function, which basically represents energy on a single frequency. If you remember anything about the Fourier transform of a cosine or sine, you know that it's concentrated on a single frequency. And we can choose the frequency. And for that, I'm going to use a variable, which I'm going to call tone frequency. So I need an entry here. Tone frequency. This is going to be of floating point type. And I'm going to do something more elaborate here. So this is the tone frequency. And I'm going to say this is in megahertz, and by default, I will give it 10 megahertz. So what happens is that the tone frequency here is in hertz. So if my variable is in megahertz, then I need to multiply by 1e6 or 1 million to convert the units. And this is very useful. You can enter any kind of expression in these fields, as I was mentioning, any kind of valid Python code, and GNU Radio will do the calculation for you anytime that tone frequency is changed. Do I want to change anything more here? No, this is great. So we need a throttle block to limit the rate at which the simulation runs. And then GUI frequency sync. I want to change this to float to match the type of the port, also 4096. And As the previous week, I'm going to be using spectrum width half, which only represents positive frequencies. We will understand why there can be negative frequencies throughout this session. Something else I'm going to use is the time sink. So this is a time domain representation. This is nothing new. This is very similar to the audio demo we had last week. And 1024 points is okay. So I'm going to call this real sampling 2, save it. And then I'm going to run it. And we can see, no surprise, that we have a single signal at 10 megahertz. And then something we might observe is this FFT plot. This is basically an FFT of the signal. It goes from 0 megahertz to 20 megahertz. And the reason is why the limit, so the question is why the limit is 20 megahertz. And that is related to the sampling rate. 20 megahertz is half of the sampling rate. So the question here is, why does this go to half the sampler rate? This is what is called Nyquist theorem, and it's something really easy to check. So what I'm going to do here is this is a middle mouse button click to get this menu. If you don't have a middle mouse button, what you can do is either to change these properties beforehand here in the configuration, or you can, where is it? Enable the control panel, and then you will get some of those properties. So I'm going to do that. And do I get it? No, unfortunately, the control panel doesn't have the property I want to change, which is the line marker. So I set it to circle. And then I didn't mention this last week, but on any of these plots in GNU Radio, we can zoom by drawing a box with the mouse. So we drag and drop. And this is like Matplotlib, for example, or MATLAB. If you have used any of those tools, you know what I mean. So what we can see here is the signal that comes out of the signal source. It is supposed to be a cosine function, but it doesn't really look like a cosine function. It really looks like a triangle wave. And the question is why? And this is just because we don't have enough samples to have something that really resembles a cosine function. So what happens is the tone frequency is 10 megahertz, and we have 40 megahertz sample rate. So in each of the periods of the cosine, we have 4 samples only. And the cosine begins at +1, so this would be the first sample. Then cosine of 90 degrees is 0, cosine of 180 degrees is -1, cosine of 270 is 0 again, and then we go back up to 1. So these are 4 points in the cosine function. And when we join these points with a straight line, it doesn't look like a cosine anymore. But even so, this really represents a cosine at 10 megahertz. It's taking the samples which are discrete in time and their values of the cosine. To see this more clearly, I'm going to reduce the frequency. So I'm going to put 1 megahertz. And since this is moving, I'm going to click stop. And now instead of only 4 points per cycle, we have 40 points per cycle. So when joining them with a straight line, this resembles more a cosine function, but it is really the same. We are taking 40 points equally spaced along the cycle of the cosine and drawing the straight edges here. So, okay, let's go back to 10 megahertz. We have something funny. So why doesn't this look the same as before? And the reason is when we change the frequency of this signal, the frequency variable here changes, but the phase, there is a phase, right? Which is internal to this block. We can change the initial phase, but then the phase keeps incrementing at the frequency we have set. So we can change the frequency, but the phase will continue in its current value. So what has happened here is we are still looking at a 10 megahertz cosine, but the phase is different from before. So rather than having the first sample where it is +1, we have it somewhere else. But you can still imagine the cosine. It would go like so and like so. Just to demonstrate, again, I'm going to say 1 megahertz, 10 megahertz, and now we get a completely different phase. It looks similar to the first one, but it's not exactly the same because these are not exactly at 0. So, okay, what I want to do is to increase the frequency of this cosine, and I'm going to make it 19, which is quite close to 20, which is supposed to be the maximum. And the question is why 20 is the maximum. So 19 looks something funny, but let me stop it. And what happens is basically we get somewhat more than 2 points per cycle. So slightly more than 2 points per cycle. Here we have 1 point. Here we have another point. And then the next point belongs to the next cycle, but it is not exactly the same phase as this one. So that's the reason why we see this strange pattern going up and down, which is also a sinusoid function. So this is what happens with 19. Let's go to 20. And with 20, as we could expect, we get only 2 samples per cycle. So we get basically 1 sample up, 1 sample down. And depending on where I freeze the phase of my signal, so this is 19, this is 20, this is 19, this is 20, I get something of different amplitude. And if I'm so unlucky that the points fall in the zeros of the cosine function, remember that the cosine function crosses 0 twice per cycle, my signal will have completely disappeared. So here we have basically some kind of problem. 20 megahertz is already a frequency which doesn't appear to be able to be represented with 40 million samples per second, because it might happen that these 2 points per cycle we have fall exactly on the zeros, and then we see nothing. But let's go to 21 and see what happens. So 21 looks very similar to 19. And if you are closely paying attention, you will see that it is actually represented as 19 megahertz here. So what is happening? The thing is that now we have slightly less than 2 points per cycle. So what happens is we have 1 point here. We have the next point there. And the following point is already on the next cycle, but it is after, so to speak, this point. It is at a larger phase. Maybe this is easier to see with one of these. Let's say that this is +1. So this would be at phase 0. This would be at 180 degrees, slightly more than 180 degrees. Let's call it 190. And then this would be at 360. So we have completed the full cycle plus 20, because if this increase 180 plus 10, this is 360 plus 20 for the sake of the example. So 360 plus 20 is the same as plus 20. And this is 0 degrees of phase, 20 degrees of phase. So every 2 samples, the phase is slowly increasing. With 19, almost the same thing happens, except with every 2 samples, the phase is decreasing somewhat. But as you can see from these plots, there is actually no way to distinguish between 19 and 21 megahertz. We say that what happens here is aliasing. So that's the proper technical term. We say that 21 megahertz aliases back to 19 megahertz because we are sampling at 40 megahertz. And the maximum frequency we can represent with 40 megahertz is 20 megahertz. We can imagine all the frequency axes going from 0, increasing, and it would increase all the way to infinity, going beyond the right side of my screen. But what happens when we have this 40 million per sample digital representation of the signal is that when we reach 20, we fold back. So we, instead of increasing, we decrease, and then 21 would be placed at 19 because going 1 megahertz up is now equivalent to going 1 megahertz down. 22 would be placed at 18, and so on. And if we go all the way up to 40, and we can see that. So let me start this again. We see a constant. We see something at 0. Why is that? Again, very easy. With 40 megahertz, we only have one sample per cycle on the cosine function. So we are sampling always the same phase. Here is something very close to 0 degrees. So we see a constant. I can change back again. So 20, maybe not 20, 13, 40. We see a different constant depending on the phase, but we see a constant. So basically with what I have said is continuing from 20 up to 40, everything goes down from 20 to 0. And then we could continue even more, and it goes reflected upwards. So 41 would be the same as 1 megahertz, 42 would be the same as 2 megahertz, 60 would be the same as 20, and you can imagine what keeps happening. If I do 61, which would be here, it needs to go to 19. So this is how digital sampling works. This is the Nyquist theorem. It tells us that with 40 million samples per second, with 40 megahertz sampler rate, we can only represent from 0 to 20 megahertz worth of spectrum. Or in general, if we sample at a rate f, we can represent from 0 to f divided by 2. Any questions at this point? This is quite fundamental about signal processing. Okay. Coming back to what I wanted to do, this is a simulation or a model of how an SDR receiver like the RTL SDR works. As long as the frequencies I put in the input are below 20 megahertz, my simulation will be accurate because these can be represented in the digital domain. If I wanted to simulate a frequency which is higher from 20 megahertz, for example, the other day we were receiving FM stations around 100 megahertz, I would need to increase the sample rate of my simulation to at least twice that frequency, so at least 200 mega samples per second, or to deal with this aliasing and basically know exactly what is happening. But for the sake of this example, we will keep using frequency between 0 and 20 megahertz. So let's think that we have this signal at 10 megahertz, and we want to receive it with the RTL SDR. But we saw in GQRX and also in GNU Radio that the RTL SDR doesn't support 20 mega samples per second. The maximum sample rate it supports is 3.2 mega samples per second. So how can we proceed now? And even this is an example, but the RTL SDR can receive signals up to 1 gigahertz point something. It depends on the exact model you have. So having something which costs only a few dollars, being able to sample at 2 gigahertz, which is what you would need to sample those 1 gigahertz signals, would be impossible. There are analog to digital converters, ADCs, which are capable of sampling at 2 gigahertz and above, but they are somewhat pricey. So how does the RTL SDR operate? What it does is to move the frequency of the signal. If we want to sample this signal with a lower sampling frequency, we cannot, but we can shift the frequency of the signal to a lower frequency, and then we will be able to sample it. So how can we move the frequency of this signal or of any other signal? And I mean, moving by doing some operation within the electronics of the RTL SDR, which here are represented by operations in GNU Radio blocks. Of course, in this simulation, I could just say this is 0.5 or whatever, But that's not the point. The point is if I have something which is really at 10 megahertz or 15 or whatever, how can I move the signal by doing some mathematical operation? And the way this is done is by generating another cosine signal in the SDR. So there is something which is called the local oscillator, which generates one of these cosines. This is done in the RTL SDR, this is done in analog electronics. So far, this is just a simulation. This is really an electrical circuit, so to speak. So I'm going to place here, I'm going to call it LO freq for local oscillator LO. Anytime you see LO mentioned when talking about radios, that means local oscillator, and we will see exactly what is that. But it is basically used to tune to the frequency you want to receive. So I'm going to place it at 9.8 megahertz, slightly below my signal that I want to receive. And what I'm going to do, just to see what happens, is to multiply these two signals. So let's run this. If some of you remember the trigonometric formulas, do I have something wrong? Yes. Yes, the frequency here, I forgot to set it to LO frequency. So yeah, now it looks better. Let me stop it. Yeah, so something else is that now I have too many plots. So what I'm going to do before explaining why we get this is to organize these plots a bit nicer, because we have two of these and two of these frequency plots. So let's do something. There's something which is called the tab widget. And the tab widget is used to create a user interface which is organized in tabs. And that is very useful when we have many plots, because we can put some of them on one tab and others on other tabs. This needs an ID, which we will be writing frequently. So it's useful to keep it short. I normally use tab. The number of tabs, just 2 for the moment. And one is going to be for the input RF, which means radio frequency signal. And the other one is going to be for something which is called intermediate frequency. If you see the term IF when talking about radios, that means intermediate frequency. And it refers to the radio frequency signal once it has been moved in frequency, usually to a lower frequency, but it could be moved to a higher frequency as well. It's moved to some frequency where it is easy to process, where process means whatever we want to do with the signal in the receiver. So we have these two tabs on the interface, but we need to assign each of these blocks to one of the tabs. And the way to do it is there is one field here at the end of the properties, which says GUI hint. This is used to select where each of the plots will go. If you don't enter any values here, GNU Radio automatically puts the plots in some position, which might not be the best. But by writing some kind of code here, you can specify exactly where each of the plots will go. So for today, I'm only going to use this notation, which means use the tab GUI widget, and tab here is the same name I have chosen, and then place it in the tab number 0. So label 0 is the first tab. I use tab at 0 for the first tab. This is in the documentation, by the way. I don't know if I have shown the documentation, maybe not, so I should do that. For many of the blocks, if you go to this documentation tab, there is a link which says visit documentation page, and you can click on it, and it will open on the web browser. My web browser is on this window, so it will open a new tab for you, and then you have the documentation for Qt-GUI frequency sync. You have an explanation of what this block does. You have the details of all the parameters. And what I was talking about specifically is the GUI hint. So there is a link to see GUI hint. And this is the syntax for assigning GUIs to certain tabs in the tab widget. So it's the same syntax I'm doing. And then you also have a syntax to assign things to basically rows and columns to define where they should go on the screen. And also something very useful, in many cases, you have an example flow graph. So if you don't know how to use one of these blocks, you can see the example, and it often makes things much clearer. So yes, this is the documentation, and it's available for many of the blocks in GNU Radio. Tab 0 to assign it to the first tab, and here I want to do tab 1 for the second tab, and the same thing for this one. So now I have 2 tabs. These entry boxes do not belong to any of the tabs because I haven't assigned them to any tab. I could do so if I wanted to, but probably it's better to leave it like so for this flow graph. So this is the input radio frequency signal. It's a signal at 10 megahertz, the same we had before. And then after multiplication with 9.8 megahertz, so remember what we are doing. We have a 10 megahertz cosine, a 9.8 megahertz cosine, and we multiply. And what happens is this thing, which basically looks like a cosine of a low frequency. And then if we zoom in, we have this cosine of a high frequency, which if I do the same thing as before, so I want circles, we basically have only a couple points per cycle. So why does this happen? I was mentioning before, if someone remembers the trigonometric formulas, this is a simple consequence. If you multiply 2 cosine functions or 2 sinusoids in general, it can be a sine multiplied by sine or sine multiplied by cosine, you get a sinusoid whose frequency is the difference of frequencies, and then you get another cosine whose frequency is the sum of frequencies. So let's see if that is true here. The difference of frequencies is 10 minus 9.8, that is 0.2. And yes, I'm getting something at 0.2 megahertz. And then the difference, the sum of both frequencies is 19.8. So this is as expected. Let's try for just another value. Let's do 9, for example. So with 9, I get this strange thing, but that nevertheless, it's the sum of a cosine at 1 megahertz and a cosine at 19 megahertz. Questions so far? Okay, so what has happened here is the original signal we had at 10 megahertz has been shifted to, let's go back to 9.8, has been shifted to 0.2 megahertz, but it also has been shifted to 19.8. We can think that whatever we had here at 10 megahertz is split into 2 copies, and one of them goes to the low frequency, the other one goes to the high frequency. We want to get rid of this high frequency because we just wanted to move this thing at 10 megahertz to 0.2 megahertz. So how do we do that? there is something called a filter, a low-pass filter in this case, which will attenuate anything which has a high frequency, and will let frequencies of low frequency pass through without any attenuation. The filters basically come from analog electronics. In analog electronics are done with all sorts of discrete components like capacitors, resistors, and even some fancier components. But we can also implement them in software using math, using GNU Radio block, for example. So here I want to use a low-pass filter. And the low-pass filter already comes with a sample rate. We need to define a cutoff frequency, and I'm going to put it at 0.5 megahertz. And I will say why in a second. And then there is something which is called transition width. What is the transition width? An ideal low-pass filter would have a gain of 1 from 0 to the cutoff frequency. So from 0 to half a megahertz. That means any signal whose frequency is from anywhere from 0 to half a megahertz would pass through this filter as if the filter wasn't there. And then it would have a gain of 0 for anything higher than half a megahertz. So any signal whose frequency is higher than half a megahertz would be completely attenuated by the filter. It would completely disappear at the output. Unfortunately, this kind of ideal low-pass filter doesn't exist. It cannot be implemented with digital signal processing, and it cannot be implemented with electronics components because it's just an ideal mathematical filter. Any kind of filter that can be implemented in the real world, either with digital signal processing or with analog electronics, will need to have a smooth transition between the gain at 1 and the gain at nearly 0. It will not have exactly 0 gain. So it will attenuate the signals by a large amount, but not make them completely disappear. So how fast this transition is from a gain of 1 to a gain of near 0 is what is called the transition width. In GNU Radio or in digital signal processing, we can make the transition width as narrow as we want, but by doing so, we will increase the number of calculations that need to be done to implement this filter. So usually we need to keep the transition width to something reasonable. I cannot put something here very, very small, like 1 hertz, because maybe I run out of memory or it would be extremely slow. This is asking for trouble. So something more reasonable is 100 kilohertz. And then I have the copy of the flow graph which I have finished, and I remember a small detail. I have used in the original flow graph an FFT low-pass filter. The difference between these two is only how the calculations are implemented. This is implemented, so to speak, in the time domain. This is implemented with an FFT. And depending on the filter parameters, one of the two might be more efficient. That means faster or take less CPU time than the other. Usually when you want some large filter, and by large filter, I mean it has a large number of taps. The thing which is behind one of these filters is a list of coefficients, which are numbers that get multiplied by the function to compute the output. So if I have many taps, if I have many numbers, then I need to do many multiplications, and that costs CPU time. So when we have a large filter, because the transition width is narrow, for example, or the cutoff frequency is very low, then we get many taps. And in this case, it turns out that the FFT low-pass filter is particularly much faster than the low-pass filter. And to run with these 40 megasamples per second, I need the FFT low-pass filter if I want to run at real time. Something else we need to set in these filters is the type of the input and output, and we can choose between complex to complex, complex taps, complex to complex real taps, and float to float real taps. These real and complex taps refers to the coefficients of the filter. I don't want to get into so much detail at this moment, but basically a low pass filter will have real taps because it is symmetric in frequency, and you can choose this option rather than complex taps. If you choose the complex taps options, the filter will work in the same way. What happens is that basically GNU Radio doesn't know that the filter has real taps, and it is performing a complex multiplication where the imaginary part is always going to be 0. So it is doing a lot of multiplications by 0 that it could avoid doing if we choose real taps. So real taps. But in this case, we have a floating point signal, a real signal, and then there is no possible confusion with complex numbers. So both of these, and this actually has a decimating and an interpolating variant. I will explain what this decimation and interpolation is in some minutes. So FFT low pass filter. This is a way of getting rid of the high frequency signal that appears after the multiplication. And remember, all of this is a simulation or a model of what happens in the RTL SDR. So in the RTL SDR, this would be some piece of analog electronics. What I'm going to do, I'm not sure if I have shown this feature, is to increase the number of inputs. Most of these plots support several inputs, so we can set number of inputs too. And then I can compare the signal at the input of the filter and the signal at the output of the filter. So let's go to the IF plot. And then this is what we see. So on the time domain, we see that now we only have the cosine of low frequency. It is shifted, and also the amplitude has changed. The reason why it is shifted is because filters usually have a delay. It depends on the implementation, but they will have a delay unless it is somehow accounted for. So basically this crest has been delayed here and so on. And the reason why the amplitude is half, I'm not sure if I've made a mistake or something, but it shouldn't. So if it is yeah, it's half. Maybe it's a bug on the FFT low pass filter because the gain here is used to change the amplitude of the output. We don't care so much about the amplitude of the signal, so this is more of a curiosity than anything else. On the FFT plot, on the frequency plot, we see here, by the way, we can click on this to enable and disable. So we can see that the signal, which is at 0.2 megahertz, is almost the same on the blue thing, which is the input of the filter, and on the red thing, which is the output of the filter, because, as I said, a low pass filter leaves the signals with a low frequency pass without any attenuation. But if we look at the high frequency signal, we can see that in the output of the filter, so in the red curve, is still present, but it has been attenuated by a lot. So this is minus 20 dBs, more or less, and this is minus 130 dBs or minus 120 dBs. It is minus 100 dBs of attenuation, which is a very large attenuation. In a realistic situation, we would have noise on the signal, so the signal wouldn't be a perfect sinusoid. There would be some noise. We would see the noise floor over here, and then we would see the noise floor here, and this signal would be below the noise floor. So to all effects, it would have disappeared completely. But since we have no noise here, we can still see it. Let's see how the filter operates in the transition region. So what I'm going to do is to keep decreasing the frequency here by steps of 10 kilohertz, of 100 kilohertz. I do 9.7, and this increases 9.6. It increases. Remember that my cutoff frequency is set at 0.5 megahertz. So by the time the signal reaches 0.5 megahertz, I would expect it to drop like so and become attenuated. So if I do 0.5, I can see a little bit of attenuation. I'm going to do 45 because the change is somewhat fast. So now there is more attenuation. And if I do 0.4, more attenuation, 0.3, more attenuation, 0.2, etc., and so on. And then this is basically more than enough attenuation. I can go to 9, but you can see that the signal stays more or less the same, or 8.9 or whatever. So yes, a low pass filter is a way to select a range of frequencies, because oftentimes we only want to process certain signals which live on a certain frequency band, and then we use some kind of filter to separate those signals from everything else. Questions here?
I guess I have a question. If you're using this in FM radio, presumably the lower frequency signal would be kind of in the audible frequency range when it's turned into sound, whereas the higher frequencies would sort of be way beyond what's audible. So does it matter in that case that you're using a low pass filter, or could you just proceed without it?
Okay, and that's a very good question. So let's pretend that here, instead of having 10 megahertz as the input, I have the FM broadcast signal we were receiving last week, which was at 98.8 megahertz. The FM signal on its own is, I don't remember by heart, but maybe 300 kilohertz wide. So that's more than the audible range. What we want to do is to shift that complete FM signal, which is 300 hertz wide. We shift it to a low frequency, but the low frequency cannot be the audible range, because, well, the lower edge of the signal, we might bring it back down to some audible frequency, for example, 10 kilohertz, or even 10 kilohertz is not audible, so 5 kilohertz. But the right edge of the signal, it would be beyond audible range, which maybe is what you were asking, really. So there is no way of making this FM signal fit within the range of audible frequencies. We just shift it to a lower frequency range to be able to sample it with the digital to analog converters on the RTL SDR. And then at some point, we need to do an FM demodulation to convert these to audible frequencies. So we will see how to do that when with the second flow graph, with the FM flow graph, and maybe it will become clearer. But yes, this is a very good question, because for simplicity here, I'm doing everything with a single signal that doesn't have any bandwidth. So it's a single CW, we call it continuous wave signal. It occupies 0 hertz of bandwidth. Basically, it's a direct delta here. But usually signals have some bandwidth. So imagine here an FM signal. Then the FM signal would be translated to a frequency range over here, which is adequate for the kind of bandwidth of the signal we want to receive. I don't know if that answers your question, Steve.
I mean, I guess to put it another way, if you left the low pass filter out in an FM radio, would you hear a difference in the audio?
It depends on which low pass filter, because between the antenna and the audio output, there are several low pass filters, and we will see where each of those are. If I left out this low pass filter, what will happen is that I'm not removing other FM stations. So let's pretend that there is another FM station which is 20 megahertz away from the station I'm tuned to. And that FM station will alias into the same frequency that I'm sampling for Nyquist theorem, as I was mentioning at the beginning. And then my signal would become absolute garbage because I would have superposition of two FM stations. And if one of them is stronger than the other, maybe you might hear the stronger station that is called the capture effect, which is quite specific to FM. But in general, you would listen noise or something very garbled.
Okay, thanks. That makes sense.
Okay, great. So we have removed this high frequency signal, and we have the low frequency signal here. And then the reason I've been moving this frequency down is because let's think about the RTL SDR. It has a analog to digital converter, an ADC, which is basically doing the same as here. The voltage of the frequency of this signal, actually, of this red signal, which is an electrical signal, comes into some piece of electronics to the ADC, and the ADC is taking measurements of that voltage. I want the circle markers. It is taking measurements of that voltage very fast, maybe 1 million times per second, maybe 3.2 million times per second, if we use the maximum sample rate. Maybe you have seen a voltmeter, so that measures the voltage of a signal. An ADC is the same as a voltmeter, but it operates very fast, and it periodically samples the signal. It takes a voltage measurement here, etc. And that's basically how we get electrical signals which are continuous in time into the computer, which can only handle discrete numbers, if that makes sense. So to represent this in GNU Radio, what I'm going to pretend is all of this is analog electronics. As I was saying, all of these signals are really voltages on a cable, so they are continuous time signals, if that makes sense. And now I'm going to pretend that I'm sampling the signal 1 million times per second. So the simulation is 40 million times per second, but we want to reduce the sample rate to 1 million times per second. In this case, to represent what the RTL SDR does, using 1 megasample per second output rate as an example, because it makes the numbers easier. The way to do that in GNU Radio is very easy. There is this keep one in n block, because what I have in all of these connections is 40 million samples per second. If I want to reduce the number of samples per second to just 1 million samples per second, that is the same as keep one sample in every 40. What this block does when set to n equals 40 is it lets the first sample pass, and then it drops 39 samples. It removes them. And then again, another sample passed to the output. 39 samples are removed. So it's basically keeping one sample every 40, as the name says. Nothing too complicated. And this represents the ADC. So let's put a note in here. I want just a single input, and then the sample rate is not going to be the same sample rate as before. I'm only taking one in every 40 samples, so the sample rate is 1 million samples per second. The same thing here. And I want to make another tab. So Let's call it ADC output. And then it might become clearer why I have used this cutoff frequency of 500 kilohertz. So with a 1 megahertz sample rate that I have in here, according to what we saw at the beginning, the maximum frequency we can represent is 500 kilohertz. So anything which is above 500 kilohertz, for example, 600 kilohertz, it might be better removed by this filter, because if the filter doesn't remove it, it will appear here, but not as 600 kilohertz, because that's impossible. It will appear at 400 kilohertz. So whatever signal I had here at 400 kilohertz will become mixed with the 600 kilohertz signal that wasn't attenuated by the filter. When we use a filter for this purpose, which is to remove signals that would be aliased by the sampling, this filter is called an anti-alias filter. So this is the anti-alias filter, and before any analog to digital converter, there is an anti-alias filter, because if not, there are signals at different frequencies that when you go to the digital domain can become aliased and they overlap, and then it's not possible to separate the two signals anymore, and basically they interfere each other. So have I set this to third tab? No. Okay, let's see how this looks like. We have the 10 megahertz input signal. This is the same as before. We have this 200 kilohertz signal. We have shifted things down by 9.8 megahertz. And then in the ADC output, why do I have two time sinks? I'm afraid I've copied twice the time sink. I wanted a time sink and the frequency sink. So second tab, one input, and then sample rate divided by 40. Something convenient to mention at this point is that many blocks in GNU Radio require the sample rate. And if we do sample rate changes by decimation or interpolation, interpolation is the opposite of decimation. It's inserting more samples between the samples we have. So by doing so, the sample rate increases. If we do interpolation or decimation, we need to keep track manually of the sample rate at each of the blocks and tell GNU Radio. So here we need to say the sample rate is my sample rate variable divided by 40, because GNU Radio doesn't know that we have kept one in every 40 samples here. Each block is independent, so to speak. So, okay, ADC output, we can see the signal at 200 kilohertz. So this is the same as here. There is a signal at 200 kilohertz. But now the frequency range goes only from 0 megahertz to 0.5 megahertz. And the reason is the sample rate is now 1 megahertz. And as we can imagine, the signal here, we don't have many points per cycle. Whereas here with 40 times as much sample rate, we have many more points per cycle, and so it looks like a smooth cosine function. But really, all the information about the signal being a cosine function is in here, even though this looks a little bit awkward. And this is more advantageous to perform calculations with the computer, because instead of having to deal with 40 million numbers per second, we only have to deal with 1 million numbers per second. So when doing digital signal processing, decimation is very commonly used to reduce the sample rate to something which is as small as possible. It needs to be large enough so that the signals we want to operate with fit within the frequency range given by the sample rate. But we can do it as small as possible in order to use less CPU. or even making some calculations possible in real time, whereas with a higher rate, they might not be possible to do in real time. And this is some kind of model of an SDR receiver, yet we have real samples at the output. I promised that I was going to explain why the RTL SDR is giving complex output samples, and we will get to that. But I think it's now a good moment to take a short break. So are there any questions before the break?
Why decimate it to 5 points per cycle on the ADC output tab rather than, I think 4 points per cycle would get you to the Nyquist frequency?
Can you repeat again the?
On the ADC output tab, if you zoom in, I think you have like 5 points per cycle, and I'm wondering why. Like, would it be preferable to get down to 4 points per cycle for the Nyquist frequency, or is
Oh yeah. I see what you mean. Yes, you can do that. In fact, you could even try to get as low as almost 2 points per cycle, so slightly more than 2 points per cycle. Here it is just for the sake of the example, and also something that this lets me do is to tune things. So by changing this to 9.7, I can place it at 0.3, or 9.6, I can place it at 0.4. So think of the last week when we saw several FM signals fitting within the same range. Having this 500 kilohertz range might make it possible to have several signals here. But yes, you're absolutely right. If the only thing I want to represent is, as I had before, what was that, 9.8, this 200 kilohertz CW carrier, anything which is above 400 kilosamples per second will suffice. Whereas here I'm using 1 megasample per second. Thanks for the question.
Thank you.
Other questions? Okay, let's resume, shall we? So something quite important we have learned is that when we multiply two cosine functions, we do some frequency shifting or frequency translation. However, the disadvantage is that we get two copies of the signal. One which is the intended frequency shift, and the other one is, let's say, an unintended signal that we need to remove with a filter. We have our simulated RTL SDR, and this is giving the real signal samples here at the output. But then we might want to shift this signal again in frequency, because there might be several FM stations, for example, which we receive at the same time by putting the center frequency somewhere in the center of all these signals. And then we might want to process each of them. So to process each of them, we basically need to shift each of them to the center. So anytime we want to do one of these shifts, if we use the same thing as before, which is multiplication by a cosine function, we will get the shift we want, but also an unintended shift that needs to be removed by a filter. And having to use a filter is inconvenient because filters are expensive, speaking about computation, CPU power. And also because think about what happens if we want to shift this signal just by very little, just by 1 kilohertz. Then the difference of frequencies will be 199, and the sum of frequencies would be 201. So they would be very close. They will only be 2 kilohertz apart. And then it will be very difficult to separate the two copies. With a filter, I can demonstrate that by doing what? By doing a very low frequency here, maybe not as low because now the two frequencies are so close together that the FFT doesn't have enough resolution. So let's do something like this. If we only want to shift the 10 megahertz signal by 50 kilohertz, then we get something at 10 megahertz plus 50, something at 10 megahertz minus 50, and having one filter which is capable of letting one of these copies pass, let's say this one, and attenuating this one is complicated. So it would be wonderful if we had a way of moving signals in frequency that doesn't give us the difference and the sum of frequencies, but only, let's say, the sum of frequencies. And with this multiplication, we were using basically the properties of sinusoid functions, those trigonometry formulas. But there is a function which has the property then that when we multiply two things, then we get the sum of something. And that function is the exponential function. When we multiply exponential of x times exponential of y, what we get is exponential of x plus y. So what I'm going to show is how this works in GNU Radio with complex exponentials. I'm going to use the flow graph I already have prepared because there is nothing new. There is nothing new really to this flow graph. I have sample rate 32 kilohertz, just the default value. 1 kilohertz and 1.5 kilohertz cosine functions. And now the important thing is these are complex. So what is a complex cosine function? It is also called a complex exponential. If you remember, there is a formula which says that exponential of the complex number I or the complex number j multiplied by x by something is equal to the cosine of x plus I multiplied by the sine of x divided by 2. So this is what is happening here. We will see that in the plot in a second. This is generating a complex function which has the cosine on the real part, the sine on the imaginary part, and both cosine and sine have a frequency of frec1, which is 1 kilohertz. And the same with this one. I'm plotting both of them also on the frequency domain, and I'm multiplying both of them and plotting to show what happens. And this is what happens, and here I'm going to disable most of this because otherwise the plot is too busy. So when talking about digital signal processing, you will often see this notation I and Q for the real and imaginary part of a signal. I means in phase and Q means quadrature. And this is just another way of calling the real and complex, the real and imaginary parts of a complex number. And what we have here is our sinusoid function of 1 kilohertz of frequency. The real part is in blue, so this is I. This is a cosine. You can imagine that the cosine starts here and does this. And then the imaginary part is the sine function, which starts at 0 and does like this. So complex exponential is basically two of these sinusoids, and they are 90 degrees out of phase. The difference between the peaks of the signal is 1/4 of a cycle. So that's how a complex exponential looks like on the time domain. On the frequency domain, we can see this is 1 kilohertz. But now our plot has also negative frequencies. And why is that? The reason is what happens is if I put here -1 kilohertz. What happens is, yes, I get the signal at -1 kilohertz, but what does that really mean? What that means is that now the red signal, so the imaginary part, is leading, so it comes before the real part. Let's do the comparison again. So with a negative frequency, red has the peak before blue. If I switch to positive frequency, red has the peak after blue. This also has to do with putting a minus sign inside the exponential function. So if you think about exponential of minus I times x, the minus isn't doing anything with the cosine because cosine of minus x is the same as cosine of x, but sine of minus x is the same as minus sine of x. Anyhow, trigonometric properties. But if you want to remember this in a graphical way, negative frequency, the imaginary part comes before the real part. Positive frequency, the imaginary part comes after the real part. And having a real part and imaginary part, which are always 90 degrees out of phase, is what allows us to distinguish negative and positive frequencies. If I have only one real signal, such as the cosine, I cannot distinguish positive and negative frequencies. This looks the same. Even the sine function, okay, this is jumping in position, but you know, the location of the time axis is irrelevant here. So I cannot really say that these are two different things. It's just the same sinusoid function, which has a period of 1 millisecond. This is why physically frequencies make only sense as positive numbers. The period is the distance between peaks. So here is 1 millisecond. It needs to be a positive number, and the frequency is the inverse of the period. So it needs to be a it needs to be a positive number. Only when we introduce complex numbers and we are able to check if the imaginary part is before or after the real part, if that makes sense with this picture, we gain the notion of having negative frequencies. So that's a way of explaining how complex signals work, why we have negative frequencies. But now for the shift in frequencies. I also have my 1.5 kilohertz signal. This is the same. This green is the real part. This black is the imaginary part. And just the same with a different frequency. And then when I multiply the two of them together, maybe I can enable all of these. What I obtain is another complex exponential. The cyan is the real part, which again is before the magenta, which is the imaginary part. And the frequency is the sum of frequencies. We can check that in this plot. So 1 kilohertz plus 1.5 is 2.5. And this always works. It is not just for this example. I can do 3 kilohertz here, 3 kilohertz I meant, and then 1 plus 3 kilohertz is 4 kilohertz. So this always works. It is because of the properties of the exponential function. So this is very useful because now instead of getting 2 copies of the signal and having to remove one with a low-pass filter, I just get my signal shifted in frequency. So for example, let's say that my signal is this one at 1 kilohertz, and I want to shift it very close to 0. What I can do is to let's say 990. So then what happens? Yes, minus 990, sorry. So 1 kilohertz minus 990 should give me 10 hertz. This is the way of moving a signal of any frequency to something which is close to 0. Just maybe for the example, it's better to make this 20 kilohertz, and then we can make this minus 19 kilohertz, and 20 minus 19 is 1 kilohertz. Okay, questions about this? So let's apply what we have learned about complex multiplication to making an SDR receiver. I'm going to save this as IQ sampling because I'm going to start with this flow graph and change a few things. So the signal that comes in from the antenna is real. This is the physical world and we cannot change that. But what we can do is to generate a complex signal here. And that might not make sense at first, since in the RTL SDR, this is an electronics component. So this is basically a cable and there is voltage here. So what does it mean to have a complex signal? It actually means two real signals. So the real and imaginary part, each with two cables. Imagine this is just a shorthand for generating two sinusoids which are 90 degrees out of phase with two different oscillators, if you wish, and each of them is going through a different cable. But for simplicity in GNU Radio, we represent that with complex signals. We know that those are two real values. So we have the two signals here, and since we are now using complex numbers, we will need to convert between floating point and complex. In GNU Radio, there are some type conversion blocks to do these conversions, and there is something which is complex to float. Also, not to be mistaken with complex to real, so I'm going to explain what's the difference. Complex to float breaks the floating point number in the real. You can see here RE for real, and imaginary part. Maybe you haven't noticed, but the ports have labels. Usually they are only shown at mouse over, but there is this view how to hide port labels. So if you want to have the port labels visible always, you can toggle this option. However, oftentimes it is not necessary because, you know, the names of the outputs are often clear. For example, first input, second input. So this breaks up the complex in real and imaginary part. This only selects the real part, and this only selects the imaginary part. And for some reason, this is called output, and this is called real. But anyhow, so complex to float. Again, in the RTL SDR, this is two oscillators, and this is two cables. So we have two cables in parallel with real voltages. Then we want to multiply as before. So multiplication. And we want to perform a multiplication for each of the two oscillators we have in here. And then we put them back together as a complex signal. So there is float to complex, which does the opposite operation. Again, in the electronics, this is still two cables in parallel. But in GNU Radio, it's easier to operate with these complex connections, because now I can change this, for example, to complex. And for the time being, I'm going to disable all of these and make one input for 1096 complex and one input here to see if we have, in fact, achieved something. So to recap, this is more or less the same as before, but for some reason having to do with this explanation about complex exponential multiplication having good properties for frequency shifting, I have converted my local oscillator to a complex function, which is really having two local oscillators which are 90 degrees out of phase. And I'm performing the multiplication for each of them. So how does this look like now? When we go to the intermediate frequency, we see something like this. And I'm going to stop it and maybe do 9 megahertz for simplicity. So 9 megahertz. What we have at the output is something at -1 megahertz and something at 19 megahertz. And the reason really is that the original signal at 10 megahertz that we had is a real signal because it comes from the antenna. So we can think of it as a cosine function. The cosine function is the same as a complex exponential of plus 10 megahertz and a complex exponential of minus 10 megahertz. So when we multiply the cosine function by this 9 megahertz complex exponential, we get those two complex exponentials shifted up by 9 megahertz. So the minus 10 complex exponential goes to -1, and the plus 10 goes to plus 19. This is not really what I wanted. What I wanted is to have this one at plus 10 go near 0. So to do that, I need to use -9 megahertz. And that makes sense. Before, there was no thing such as -9 megahertz in the real signal source, because for real cosine, the negative frequency is really the same thing as the positive frequency. But now we have a complex local oscillator, so it makes sense to set it to 9 megahertz. And now the signal that was at 10 megahertz has ended up at 1 megahertz, and the mirror signal, so to say, that was originally at -10 megahertz has ended up at -19 megahertz. Why have I insisted in shifting this signal from 10 to +1 rather than the one which was at -10, shifting it to +1? For example, I could also do that by doing 11 megahertz, I think, or something like that. Yeah, it looks the same because the one which should go to 21 has aliased to -19. So that's a good point. I should also explain that in a minute. But let me get back to why -9 and not 11. The reason is, imagine that my signal wasn't just a CW signal. Imagine that it was something else, for example, two signals, one here, one slightly above it, of a different amplitude, for example. Then on the mirror signal, so let's pretend I'm not moving things. So we have something here, something slightly above it. On the mirror signal, we have something here, something slightly below it, because this is mirrored. This is +10, this is -10. If we have 10.1, let's say, then we have -10.1. So if we move this part of the signal close to 0, basically we are getting a mirrored version of the signal. The signal which was a lower frequency will appear on the right. You can, as an exercise, you can put together here multiple cosines. You can add them with the add block and see what happens to really convince yourselves that the best thing to do to avoid getting confused is to move this signal at a positive frequency close to 0 rather than this at a negative frequency. Otherwise, we get everything mirrored in frequency, and that is easy to fix. We can use the complex conjugate. That's also something for another day. Why taking the complex conjugate of a complex signal performs frequency inversion or frequency mirroring. But anyhow, for today, it is good enough to say that we want to mix with -9 megahertz or -9.5 or -9.8 actually is what we had to bring this to 200 hertz, 200 kilohertz. We still have this additional signal we need to remove with low pass filter. That is inevitable, and the reason is that to begin with, we had a real signal because it came from the antenna, it came from the physical world. So I need to get my filter again, and now I'm going to make it complex real taps. Put it here, connect it there, and let me see. Yeah, 2 inputs. Two inputs on this one. And now, yes, I'm going to change the default also because I said we want to mix with -9.8. So again, the filter removes the high frequency signal, and in the filtered version of the signal, we only see the thing which is at 200 kilohertz. The other one is highly attenuated. And what we can check is that now, as before, if I set the filter to -9.5, -9.4, the filter signal starts to disappear because the cutoff frequency for the filter is at plus 500 kilohertz. But also something else is that now we can have negative frequencies as well. So if I do -10, the signal goes exactly to 0 hertz. This is also called as DC. DC means direct current. So in electronics, we say that there is direct current when the signal is steady and it doesn't change. So if you see DC, it means the same as 0 hertz. But we can also go past DC to negative frequencies. And this is at -100 megahertz. As before, as in the complex multiplication example, this means that now the imaginary part, which is this black line, is before the real part, whereas for positive frequencies, it was the other way around. And we can also continue, and this is -10.3, so this is at 300 kilohertz, -10.5, and what we see is that the filter is symmetric in frequency. So the cutoff frequency of the filter is from -500 kilohertz to +500 kilohertz. That is the frequency range that the filter lets go through. And in fact, if I continue to -10.6, now the signal is at -0.6 megahertz, but it is heavily attenuated. Okay, any questions at this point? Okay, so the only thing that remains is the ADC. This is again, keep one sample every 40, but now they are complex samples. And this is really what the RTL SDR is giving me. These are the complex samples that we get from the RTL SDR in GNU Radio. We understand where they have come from. Each of the two real numbers in the complex number, so the real part and the imaginary part, comes from multiplying the radio frequency signal on the antenna, which is a real signal because it's a voltage from the real world, by two local oscillators which have the same frequency and have 90 degrees phase difference. So we might think about it as a complex local oscillator, but just as a shorter mathematical representation for it. And then we have done the multiplications and assemble everything as complex numbers. And why is this advantageous? Well, the reason this is advantageous is now I'm getting a complex signal here. So if I want to move this in frequency again, this now is a complex exponential. It is not as here where we had a real signal from the antenna. Now we have a true complex signal. And if we want to shift it again by whatever amount, we can do that with a complex multiplication, as in this example, and we don't need to filter anymore. And I can show that real quick. So let's put 199, maybe minus 199, for example. And second input. So I can perform this multiplication. This looks a bit confusing. What happened? Yes, I wanted. This is what I mentioned about you need to specify the sample rate to each GNU Radio block, and you need to keep track of the sample rate manually. This block, the correct sample rate is not sample rate, which is 40 megahertz, but rather sample rate divided by 40, because we are after this decimation by 40. It's the same as here and here. So now, yes, now I'm getting the signal I expected. So I have my signal coming from the RTL SDR on the USB port, let's say, at 200 kilohertz. And then I shift it down by 199 kilohertz. So it ends up at 1 kilohertz, for example, if that's what I wanted to do. And I only get one copy of the signal rather than two. I do not need to do any filtering. So that's the reason why complex numbers are so common in digital signal processing, because it is so much easier to shift in frequency complex signals, and shifting signals in frequency, it is a very common operation. And complex numbers are so useful that they are even built into SDR receivers in this way. So the RTL SDR is built in such a way that it already gives us complex numbers at the output. I hope this makes sense. If it's the first time you see it, it might be a bit confusing. It is really something you need to think about and interiorize these concepts. But really the bottom line here is when we have complex signals, it is easier to move them in frequency. And so many SDRs are built in such a way that they give us complex signals, where complex really means this thing. Relating this back to the physical world, basically what this means is that the center frequency we have here, so 0 megahertz, is not actually, yeah, another way of saying it, the center frequency we have here, which is 0 megahertz, actually corresponds to the physical frequency 9.8 megahertz. Why? Because we are tuned to 9.8 megahertz by setting our local oscillator to minus 9.8. In fact, we can do that in GNU Radio. We can basically change the labels of the frequency plot. So there is center frequency here, and I can set minus local oscillator frequency multiplied by 1/6 because it needs to be in hertz. So if I go to this plot, this only changes the x-axis of the plot. But now we see this corresponds to a signal that was at 9.8. Okay, not this because this is something I have shifted in frequency just because I wanted, but this at 10 megahertz is the same as our original signal at 10 megahertz. And if you remember GQRX, it was showing us the proper frequency axis. So when we tuned to some FM radio station at 98 megahertz, it showed 98 megahertz on the frequency axis rather than -2 or whatever. But the frequency for the samples we are getting on the USB connection is -2 or -1 or +1 or something small because it has been down converted. The technical term is down converted or shifted down in frequency. So really the ability to tune to a center frequency and have some signals which are to the left of that frequency, which are negative frequencies with respect to the center, and signals to the right, which are positive with respect to the center, is the advantage of complex signals. Questions about this? Okay, so this is what I had regarding IQ sampling and sampling in general. I also have the FM broadcast example. Since we still have 20-ish minutes, I'm going to get started with that example, but probably I will not have enough time to finish it. So I will do half and then the next half for next week, and we will basically recap and complete the example. But this will also be good to introduce some other GNU Radio blocks which are related to what we have seen. So if you want the finished version of the flow graph, this is in the FM broadcast. What I'm going to do is to copy some of that because it's basically the same as we did last week. So more zoom. And then sample rate. So what do I have here? I have, it's saved before. I have the RTL SDR source. I'm using this particular block. You might remember that there is the RTL SDR source and also the, oh, sorry, this is not the one from last week. So this is the one from last week. And there is the RTL SDR source and the SOPI RTL SDR source. Any of those will work for this example, which I think I've done something wrong. So FM broadcast 2. I have set the center frequency to 98.5 megahertz. Now we know what that means. It means that whatever is at 98.5 megahertz on the RF spectrum will end up on the center, will end up at 0 on this complex sampling because this complex multiplication is shifting everything down in frequency by 98.5 megahertz before doing the conversion to digital samples. I also have the ARF gain. 30 is a good value, but I have this entry to change it if needed, and I need to plug in my RTL SDR for this to work. So yeah, we see the same FM radio stations as last week. Something else I have done here is on this, I have set the average to low to avoid having the signals jump up and down so much. So probably the first thing I should start with is how to record a signal with GNU Radio, because I have shared the recording for those of you without the RTL SDR. And now I'm going to explain how to do the recording and how to read from the recording. So there is the file sync block. I think I mentioned this last week, but what I didn't mention is how to make a recording of a specific length. Because if I hook this up directly and press play, it will keep writing to the file, and at some point the disk might become full, or you might get a very large file or whatever. So often we want to limit the number of samples we record to file. So for example, in this case, we want to make a 10-second recording. I'm going to use a variable for the recording duration. 10 seconds. This block is called head, and it is called head because in Unix there is a command which is called head, which only lets through, or it only outputs the first n lines of a file. So if you say head 10, for example, it will only spit out the 10 first lines of the file. So in the same spirit, this head block only outputs the first n samples. So for example, head 1024 means the block will only output the first 1024 samples. And then it will say, I'm done, please stop the flow graph. So to record for 10 seconds, what we need to do is to multiply the sample rate, which is the number of samples per second, times recording duration. And depending on whether this sample rate is a real number or a floating point number, you might need to round this if you get any errors. And you can check, and this is 32 million samples. So that's what we need for 10 seconds. And then I click here, play. And we can see the signals. And the file is being recorded to disk. And in 10 seconds, everything will stop. Here it is. So now everything has stopped. And the reason why everything stops is because this head block says that it is done. It is not accepting any more data. So when you have a connection in GNU Radio, the same data is delivered to all the blocks that are connected to the same point. So for example, these two blocks get the same data. So if head is done and isn't accepting any data, this frequency sync or anything else you have connected to the same point will not get any data as well. So this is how you make a recording. There are some applications which you can use to investigate a recording. You can even open it in Python. So maybe I should show that. If I import NumPy, not this one, but FM recording, and then the D type, you know, there is this D type parameter is complex 64. So complex 64 means it's 64-bit complex numbers because they are 32-bit floating point numbers. So this is the way you get your data into Python, and you can do something like show me the first 100 complex samples, and you can see these are all complex numbers. I'm showing this because I know many of you work in Python, so if you have some code and want to process some data you recorded with GNU Radio, you now know that it's very easy to do it with NumPy, and you can also plot things. So if you want to plot the first 1,000 samples, you can do it as so. And yes, it's impossible to tell that here there are several FM stations, but if you do more NumPy operations and do some FFTs to represent things in the frequency domain, then you will be able to see something quite similar to GNU Radio. Something else you can use is in Spectrum. This is easy to install in Linux. Probably it's also easy to build it in macOS. In Windows, maybe it's not so easy. So here you get a waterfall display. So time axis is the horizontal axis, frequency axis is the vertical axis, and you can see the FM radio station. Something you need to enter here is the sample rate, otherwise the frequency scale will be wrong. And you can play with the parameters. So for example, the FFT size to decide how to represent things, but here you can see the different FM signals. And there is something else called IQ Engine, which is a web application. So you can access that from your web browser. Maybe next week I will show how to use IQ Engine. So that might be a useful alternative to in Spectrum, especially for those of you who aren't using Linux. So that's a recording file, and on Slack you have the link to a Google Drive with a very similar recording to this one. Now we want to read the recording in GNU Radio. So the way to read one of these files is with the file source. That's basically the same as the np.fromFile command we use in NumPy. We need to go and specify the path of the recording. And then there is this parameter which says repeat yes or repeat no. If we say repeat no, let's see what happens. We, I don't know why this stops immediately. Oh yeah, I know why this stops immediately. So if we play a recording, and I think this is missing from the blog I have online, from the flow graph I have online, yes. Throttle block would be needed in some cases. So if you have a recording and don't want to play it instantaneously or very, very fast, but in real time, then you need a throttle block. So if we include a throttle block, the recording plays in real time. We see the same thing as before, as expected. And in 10 seconds, it will stop because this is the end of the recording. And if we set it to repeat, then basically it will repeat forever. So those of you with the RTL SDR can follow along this part of the tutorial using the RTL SDR. Those of you without the RTL SDR can download the file, use the file source, and usually a throttle block, although it will not need it at the very end. I will mention why. So basically you have these two alternatives. What's the first thing we want to do? The first thing we want to do is that here there are multiple radio stations, and we want to receive this one. And by receive, I mean listening to the audio in this station. This is a classical music radio station, so we want to listen to that classical music. So the first thing to do is to move this signal to the center, to 0 hertz, to the DC frequency, because that's the way in which most operations work simpler, so to speak. When you want to work on a certain signal, you usually shift it to the center. And we also want to get rid of everything else, because if we don't remove the rest of the signals, they will interfere with our signal here, even though they are at different frequencies. So the way to move this signal in frequency to 0 hertz, we already know. It is a multiplication by a signal source which generates something at a frequency of minus 300 kilohertz. And then I can put here 2 inputs. And show how the signal of interest is now in the middle. And everything else has been shifted by the same amount. And something else I should have given more emphasis before is what happens when you reach the edges. So here we are shifting everything 300 kilohertz to the left. This has gone here. But what happens, for example, with this thing? Well, it's actually here, but then when we move past the left edge, it comes back again on the right edge. So this is how aliasing works for complex sampling. With real sampling, we saw that when we reach the right half, things start mirroring down. So we go like this, and then we mirror down, and then we kind of rebound at 0, and we keep going like this, back and forth. But with complex sampling is somewhat different. So what happens is when you go through this edge, we appear on the other edge, and we can continue, and we can continue indefinitely. So, but going in one direction, it's the same. If we shift it to the right, everything which goes out of the right edge will appear again on the left edge. So hopefully that is clear. Also something important to point out, which I didn't make enough emphasis before, with complex signals, we have twice as much spectrum. So here we are sampling at 3.2 megahertz, and the bandwidth we have is from minus 1.6 to plus 1.6. So rather than going from 0 to sampling frequency divided by 2, it goes from minus sampling frequency divided by 2 to plus sampling frequency divided by 2 for a total bandwidth of sampling frequency. And the reason for that is because we have negative frequencies and positive frequencies, and those are distinct. Whereas in the real case, with real signals, the negative frequencies and the positive frequencies are not really distinct. They are mirror images of one another. So we have the FM station here. Something which I was speaking about before from memory is the bandwidth of one of these signals. We can see that it goes more or less to plus 100 kilohertz and also to minus 100 kilohertz, slightly less, but let's call it 100 kilohertz. So the total bandwidth of the signal is about 200 kilohertz, more exactly 190 or so. So we want to filter this signal, or another way of saying it, we want to filter out everything else. We know how to do that. I'm going to use a low-pass filter. And the cutoff frequency is going to be 100 kilohertz. The transition bandwidth is going to be maybe 25. kilohertz. And then we can see that now the red signal, which is the output of the filter, only contains the FM station of interest. The rest has been attenuated heavily. It's still present. So for example, this signal is here, but the power is much smaller than the one of the signal of interest. Okay. I think this is a good point